Hello everyone, my name is Priyanka and I welcome you all to my session. So today's question says, a voltage V is equal to V naught sine omega t is applied to a series LCR circuit. Derive the expression for the average power dissipated over a cycle, and under what condition no power is dissipated even though the current flows through the circuit, and the second is the maximum power that is dissipated in the circuit. Alright, so here let the alternating EMF applied to the RLC circuit be E is equal to E naught sine of omega t. If the alternating current lags behind the applied EMF by a phase angle of phi, then I can be written as I naught sine of omega t minus phi. Alright, so power at any instant of time, power is given by dw by dt, where w is the work done, which is equal to E into I. So we can write dw by dt as E naught sine omega t into I naught sine of omega t minus phi, which can be written as E naught sine of omega t into I naught. I am opening up the brackets for sine a minus b, which says it as sine of omega t cos phi minus cos of omega t sine phi. So just opening up the brackets, E naught I naught sine square omega t cos phi minus E naught I naught sine omega t cos omega t sine phi. So here we can see these two terms, sine omega t cos omega t. I am just going to assemble these two terms. So I naught E naught I naught sine square omega t cos phi minus E naught I naught by 2 sine twice omega t cos phi. So it is dw. What I am going to do is that I am going to multiply these two terms by dt. So now we have to do the integral of these terms from 0 to t. So total work done over that complete cycle, let me just put in the blocks so that there would be no confusion. So total work done, W, can be written as integral of E naught I naught sine square omega t cos phi into dt minus integral of E naught I naught by 2 sine twice omega t into cos phi into dt. So I am just going to put out all the constants. So E naught I naught cos phi are the constants here, and E naught, these were the, just a second, I'm going to remove them. So here we are left with cos sine square omega t dt. So that's a derivation that is involving a lot of trigonometric concepts. So please just try to understand what's being done. So here I'm taking out all the constants. So we are left with integral of sine twice omega t into dt. Okay, now we are knowing that the integral of sine square omega t comes out to be t by 2, that is E naught I naught cos phi into t by 2, and the integral of sine twice omega t comes out to be 0. So we just left with the term work done, which is equal to E naught I naught cos phi into t by 2. So that's our work done. So this was work done. However, we are knowing that power is equal to work done upon time. Therefore, power is equal to E naught I naught cos phi into t by 2 divided by t. So, power can be written as E naught I naught upon 2 into cos phi. Also, making it right further, it can be written as root 2 into I naught by root 2 cos phi. Therefore, we can write it as EV into IV cos phi, where EV and IV are the virtual EMF and current. So, this was the total power of the RLC circuit. Now, let's discuss about the further subparts of the question, which is under what condition no power is dissipated even though the current flows through the circuit. That means when the power is supposed to be 0. When is the power 0? So, we have to make our cos phi term 0. That means phi has to be 90 degree. So, under the condition when the angle phi is 90 degree, the power is going to be 0. The last part is about the condition when there is the maximum power dissipated in the circuit. So, our cos phi term has to be maximum. So, when is cos phi maximum? So, we need our P to be max, which implies phi to be equal to 0 degree when cos phi will be equal to 1. So, these are the two conditions: when phi is 90 degree, power dissipated is 0, and when phi is 0 degree, power dissipated is maximum. So, that's your derivation for the power, the average power dissipated over a complete cycle of an RLC circuit. So, hope I was able to make you clear with all the concepts. Thank you so much for your time. Have a great day. Bye bye.